Hello everyone, this is Dr. Lennon, and today we're going to be talking about 17.1 lines and angles and also 17.2 polygons. So this is building our way towards trigonometry and looking at some of the fundamental properties of some geometric shapes. So let's go ahead and just talk about essentially angle measure, and then we can also talk about some areas and parameters today. So let's start with the definition, kind of a naive definition here. So the angle is the size of the opening between two intersecting lines. So there's two primary ways to measure the size of an angle. So the first way is, in this section we'll just look at measured in degrees. Later when we talk about circles, we can introduce another way to measure them, so I'll talk about that. So later, also measured in radians. So let's just kind of think about that. Well, basically one full rotation, the number of angles in a circle, if you look at a circle, and you have the center and the radius, if you go one full rotation, this has a measurement of, so this measures 360 degrees. So this actually comes from the ancient Babylonian system of measurement. So the reason they chose 360 was they worked in a base number system, and that is a multiple of 60. And then also, if you looked at, say, just a quarter of a circle, 1 quarter turn. Well, actually, why don't we introduce first the straight angle? So you can kind of determine degrees once you know the circle by just looking at all the subdivisions. So if you just go straight across through the center diameter of the circle, this straight angle has a measurement of 180 degrees. So we use that quite a bit whenever we're looking at lines. If we have some, so let's say we have some angle, some straight line, and then we have something that cuts across it, another intersecting line. So if you had A and angle B here, then we would know A plus B, since they form a straight angle. If you add these together, they have to add up to 180 degrees. And then we can subdivide degrees into even smaller parts. Again, those are in, so they're in proportions of 60 as well. So 1 degree is equal to 60 minutes. So that's what we say here, 1 degree equals 60 minutes. So we use a kind of prime to denote that. And then if you want to go smaller than minutes, 1 minute is the same as 60 seconds. So this is 1 minute equals 60 seconds. So we also have some names to denote the size of these types of angles. So in terms of types of angles, we say an angle is acute if it measures less than 90 degrees. So acute means the angle is less than 90 degrees. Obtuse would mean it measures more than 90 degrees. A right angle has measurement exactly 90 degrees. This is known, if you write that, this occurs when you have perpendicular lines. So, and perpendicular lines, if they cross at a right angle, are usually denoted with a little box at one of the vertexes of intersection there. And then the last one that we talked about also, we said the straight angle measures 180 degrees. All right, so let's continue. So we have some kind of facts from geometry that allow us to solve for missing angles and problems if those come up. So, so let's say propositions. So, these are just kind of facts about angles. So the first one, so vertical angles are opposite angles of intersecting lines So the fact there is vertical angles have the same measure. Two, if you have parallel lines, cut by a transversal, then corresponding angles are equal. So let's just look at an example. So, sorry, I didn't mean to put that dot there. So parallel lines means they don't intersect. So if we have a line here, and then maybe also a line here, a transversal is just a line that cuts across it. Corresponding angles have to have equal measures. So let's say we label the angles as follows. I don't know, A, B, C, D, E, F, G, and H. So if they're at the corresponding intersecting vertices, they're corresponding. So basically, angle A is going to be congruent to angle E, which, yeah, so those are those two corresponding parts. You have angle B is in the same place. Sorry, so this squiggly followed by an equal sign is just the geometric symbol for congruent, meaning that they have the same measure. So angle B is the same as angle F. Those are corresponding, and then you have two other pairs. So we would also have that C corresponds to E. C corresponds to G, and D would correspond to H. So all of those angles have the same measure. And maybe one more fact about these things that comes up a lot. So the interior angles of a triangle add to 180 degrees. So probably you know that. In general, there's a more specific theorem for general polygons. So I'll write it down, but triangles are the most frequently encountered. We could also say, given a polygon with n sides, the sum of the interior angles turns out to be n minus 2 times 180 degrees. So you can see that's true. A triangle has 3 sides, so 3 minus 2 times 180 is 180 degrees. If we did it for a rectangle has 4 sides, so 4 minus 2 times 180 would be 360 degrees, and so on. So let's go ahead and look at some examples where we're just solving for the missing angles. So example, we want to solve for the missing angles. So let's suppose we have a collection of maybe just 2 intersecting lines. So we have some angles like this. Again, these are not necessarily drawn to scale. I'm just kind of more focused on worrying about the properties. So say we have A, B, and C. Well, we know B has to be equal to 143 degrees by vertical angles. And then we know A plus 143 is a straight angle, so A plus 143 has to equal 180 by the straight angle measurement. So then we can subtract 143 on both sides. So, whoops, zoom too far out. So A would turn out to be 37 degrees. And then we know, if you look at the picture, A is a vertical angle with angle C. So C has to also equal 37 degrees by vertical angles. So these are the missing sides we've identified in this example: B 143, A 37, and C 37. B, maybe we have, just a straight angle here. So maybe we have something like, we have this angle 143, and we have this side as X. So we know, again, by straight angles, 143 plus, well, actually that's, oh, I meant to write 104. I copied the same number from the previous problem. Seemed a little suspicious to me. So we have 104 degrees right here. So we know 104 degrees plus our angle X has to add up to 180 degrees. So subtract 104 on both sides. And we know that X has to have measure equal to 76 degrees. I will make one kind of comment. A lot of times when people talk about the measure of the angle, sometimes they label just the vertex of some side, and if you want to indicate angle, so let's just make a comment notation. Often people will write, let's say, angle X instead of X. To identify the object as an angle. When the context is clear, I will just omit the angle symbol. So I'll leave that off when it's clear, as it has been for the past couple. It's just normally a little bit of extra writing. Okay, so let's continue with this example. Let's look at, maybe we have a triangle. So this is an isosceles triangle, so we haven't covered what that means yet, but isosceles just means either the base sides, so it has either 2 of the same side length measures or 2 of the same angle measurements. So because you know that the 2 base angles both have measurement A, they're equal, So that makes this an isosceles triangle. So we'll cover that in a little bit more detail in the triangle section coming up. But basically we know that the sum of all three angles of our triangle have to add up to 180. So a plus 48 equals 180. So that means 2a plus 48 equals 180. And then we can subtract 48 on both sides. So doing that leaves us with 2a equals 132. And then we can divide by 2, not by a. Apologies. And we will be left with a having measure 66 degrees. And then D. Let's do one great big example with parallel lines here. So these lines are parallel. A lot of times to indicate that two lines are parallel, they might write little arrows somewhere in the middle. So that indicates that they're parallel. Anyhow, for us, we've got this transversal. So let's say that this has measure 65 degrees and we want to find the missing angles. Say, I don't know, A, B, C, D, E, F, and G. So we've got 7 things to figure out in this problem. The first thing to figure out, F is a vertical angle with the one known angle 65. So F has to be 65 degrees by vertical angles. And then G has to add up to, so if you do 65 plus G, that has to add up to 180 by straight angles. So that means if you subtract 65, G is going to be 115 degrees. So I've got angle G. Okay, is angle G vertical angles with anybody? Sure, G is vertical angles with C. So C equals 115 also by vertical angles. So C is 115. Can we figure out F? Well, F makes a straight angle with C. So C plus F has to equal 180, which means C, oh no, we have F. We already have F. So we have C, G, and F. So we have the top 4. Now we need to go to the bottom 4. So we know angle B corresponds to the first known angle, 65. So we can say B equals 65 degrees by corresponding angles. So B equals 65 degrees by corresponding angles. In fact, we can actually get all of the last 4 by corresponding angles. E will correspond to G, A will correspond to C, and D will correspond to F, as we spoke about earlier. So if we can just write those down, we can do all of the last by corresponding angles. So we know A equals 65 degrees. A equals 115 degrees because it corresponds to C. So A is 115 by corresponding angles. So A is 115 as well. What else do we have? D corresponds to F, so that makes D 65 degrees. So D is 65 degrees by corresponding angles. And then we have one last one that we can do by corresponding angles. So once you get the top 4, you can do the last 4 all by corresponding angles. So E will correspond to G, which is 115 degrees. So basically all the angles that we're seeing up there are going to be either 65 or 115 of the 8 angles formed by the 2 parallel lines and the transversal. Again, the thing that makes this go, the last 4 that we figured out with corresponding angles, is all because we had a set of parallel lines cut by a transversal. Okay, so that's it for essentially the geometry stuff that we wanted to remember in terms of just basic angles. So let's move on to the next section. Let's go on to 17.2 polygons. So basically we're going to focus on two concepts here, areas and perimeters. So first let's talk about perimeters. The perimeter of a polygon is the length of the sides added together. So sometimes you'll see them in the textbook write down some formulas for these things, but really there's nothing too complicated about figuring out a perimeter type of situation. You just add the sides together. So if you have a triangle, add all three sides. If you have something like a rectangle, you may hear them say 2L plus 2W, but that's just because the lengths and the widths are both going to be the same. So you have two pairs of sides that have the exact same measurement. So example, let's start by computing the perimeter. For circles, so circles is another section we'll look at. Rather than using the word perimeter in circles, they use the word circumference. So that's one thing to keep in mind. So let's say find the perimeter of each figure. Or of each polygon. So let's say we have some, maybe this is a trapezoid. It doesn't really matter so long as you know all four lengths. So let's say this is 36 over here. We've got 28 on top, 43 on bottom, and let's say 20 on this side. So, I mean, you might have some unit of measurement. Whatever your unit of measurement is for the side lengths, the perimeter is also a length. So if these were all measured in feet, the perimeter would also be measured in feet. So our perimeter here, which we'll just denote with capital P, is 36 plus 28 plus 20 plus 43. And I believe that adds up, let's see, 6180. So 36 and 28 is, that's 64. 64 and 20 is 84. And 43, is that 127? Sorry, let me, no, that's way too small. 36 plus 28 plus 20 plus 43. Yeah, no, it is 127. So there we go. Again, that would have the same unit measurement if there were something describing it. So one that is maybe a little bit interesting is if we look at this figure, let's say it's kind of like an L shape. And let's assume these are all right angles. So we'll indicate that all of these are right angles, all the angles in the figure that we see. And maybe we don't know all the parts. Maybe we know that the length here is 18 and the top is 11, and we want to know the perimeter. Well, the problem is we have a bunch of unknown sides. We don't know this side right here, maybe we'll call it X, and we also don't know this one right here, maybe we'll call it Y, and then we also don't know this one, which is, I don't know, let's say A, and then maybe we also don't know the width here, which is B. But the thing is, what do we know? Well, we know how much X and Y have to add together. So we might not be able to describe exactly how they separate the 11, but you know that X plus Y has to be the same as the top length because of the perpendicular angles, so that it has to be 11. And also we know that A plus B has to be equal to 18. So our total perimeter here, we know that we can actually just take 18 plus 11 plus another 18 plus 11, and that will give us the total perimeter of our figure, which is 36 plus 22, which is going to be 58. So our total perimeter here is 58. So sometimes you can figure out perimeters without even being able to identify all the sides. So I don't know, you can also look at other ones, and these will come into play maybe more when we learn about things like the Pythagorean theorem. So say we had some triangle, I don't know, say this were 3, 4, and 5, And maybe let's make these inches. So triangle with 3 inches by 4 inches by 5 inches. Again, our perimeter here is just 3 plus 4 plus 5, which comes out to 12 total inches. So nothing too crazy there. Okay, so let's talk about area. So the area of a polygon is the number of square units of measurement it contains. So you can imagine if you could somehow draw a grid of a bunch of, say, 1 by 1 squares on the inside and count those all up, that is the area of that polygon. Now, that's not practical to do in many cases, but there are several formulas that we know if we so happen to know some of the side lengths. So let's look at some formulas. So for squares, rectangles, and parallelograms, we know that the area is just equal to the base times the height. So a lot of times with rectangles we say length times width, but with a parallelogram looks something like this. It might have parallel sides. So the point is this side is parallel to this side, and then the top is parallel to the bottom like this. Knowing the side lengths won't help. So this length right here might be the base, but this slanted thing right here is not the height. The height is actually going to be the thing that would be perpendicular to it. So you'd have to know the height there for something like a parallelogram. Whereas since the rectangle forms a 90-degree angle, there isn't really a slanted length that you have to worry about. That just turns out to be exactly the height. Okay, so we also have an area formula for triangles. So we know the area for a triangle is 1/2 times the base times the height. So you multiply those 3 together. And then maybe one other one we'll look at is the trapezoid, which is a different kind of quadrilateral. So how do we figure out the area of a trapezoid? Well, what does a trapezoid look like? Well, a trapezoid has one pair of parallel lines. So in this case, let's say the top and bottom are parallel, but the other ones are not. They would intersect if they continue. So this is parallel to this. So if we identify that with base 1 and the top, let's call base 2, then again, if we have the height, the area formula here is essentially, I think of it as if you could somehow smush this together into a rectangle, how wide would it be? Well, that would basically be about the average of the two bases. So what you do is you take base 1 plus base 2, you divide that by 2, that gives you the average base length, and then you multiply that by the height. And that is the area formula for the trapezoid. So let's put these things into practice. Again, it's just about recognizing the correct figure and then identifying the formula that we need to plug things into. We'll have a lot more interesting ways to find some areas once we learn a little trigonometry. But let's just focus on the basics now. So let's say find each area. So let's say we have a rectangle, almost looks like a square, but again, these things are not necessarily drawn to scale. So this is a rectangle because we know it's a 90-degree angle that it's intersecting at. Technically, all 4 of these will be right angles, all 4 vertices, excuse me. So the area here is just going to be that 21.6 times that 17.5. So if you use the calculator to multiply that out, you end up with just 378. But both of these were measured in inches. So if this is 378, since you're looking at all the square kind of 1 unit boxes that fit inside it, the units of the area here are not just going to be inches anymore, but they'll be inches squared. So sometimes they'll write a little exponent 2 with the inches, or I often see 378 and then they'll write SQ period IN period standing for square inches. So the units for the area are going to be different than the units for the measurement of the sides. B, let's go ahead and look at maybe a trapezoid example. So let's say we have this is a trapezoid, and let's say this is a 90-degree angle, so that we know that actually the top side, this 36 that I'm writing there, that is going to be the height of the figure. So the bases are always going to be the parallel lines. So that's what you want to identify as the bases, the parallel sides. So you don't have to worry about orienting it. So let's say the first base is 36, the other base is 21, and then the slanted side is 39. So what do we do for the formula here? Well, this is a trapezoid, so we want to average the bases. So we do 36 plus 21 divided by 2, compute that quantity, and multiply it by the height, which is the side it makes a perpendicular angle with, which is 36. So when you multiply that out, again, let's go ahead and do that. And multiply that by 36, so we get 1026. I didn't include any units here, but let's go ahead and kind of do some in hindsight. Let's say these were all meters. Then the units of the area would be square meters, or as we said before, we could write those as square period, meter period. So both of those you will see. Okay, let's do one more, or maybe we look at the area of a triangle. So let's say we have some right triangle, and let's say it has measurements, I think, so let's say this one is 7, this one is 24, and this one is 25. So what are we identifying as the base here? Well, the base is 7. And why don't we give them, I don't know, a unit also. Why don't we say feet? So 24 feet, 25 feet, and 7 feet. So in this example, our base is equal to 7 feet, and our height is equal to 24 feet. The angle opposite the right angle, 25, is, or the side length opposite the hypotenuse, opposite the right angle, is known as the hypotenuse. And we'll talk about that more when we get into the Pythagorean theorem. So here our area is 1/2 times our base times our height. So 1/2 times 24 is 12, and 12 times 7 is 84. So this should be 84 feet squared, or 84 SQ period FT period. Okay, so that's it so far for the basic angle measurements and some perimeters and areas of polygons. So next time we'll do the same, but we'll look at circles, and then that way we can introduce some radian measure, and we can also talk about the Pythagorean theorem for triangles, and that will wrap things up for this week. So this is Dr. London signing off, and I will talk to you again on Thursday.